Hello viewers, today in this part of the session we will be discussing about photodetectors, and the brief outline for today's discussion is as follows. We will start the discussion to know little bit about photodetectors, then we will discuss about thermal detector and one of the examples of thermal detector, that is bolometer. Then we will discuss about photomultiplier tube, which is a device which detects photons. Then we will go to the next device, that is also a detector which detects photons, that is charge coupled devices. Then we will discuss the different types of photodiodes, that is PN photodiodes, PIN photodiodes and avalanche photodiode. And finally, we will discuss the very important properties of photodetectors, that is quantum efficiency and responsivity. So, what is a photodetector? It is a device which converts a light signal to an electrical signal, such as voltage or current. And in many photodetectors, this conversion was achieved by the creation of free electron hole pairs. This happens by the absorption of photons and creation of electrons in the conduction band and holes in the valence band. So, when you have a p-n junction device for understanding a photodetector, it could be the basic device that can help us picturize the whole physics that is going on in the photodetector. So, when we shine light on the junction of the photodetector, electrons from the valence band will jump over the energy gap and go to the conduction band, and in this process there will be a hole which will be created in the valence band, and this hole and electron pair, they are not isolated. There is a Coulombic interaction between them which binds them, and that is why we call them electron hole pairs. Now, the high speed and high sensitive photodetectors are having a p-n junction in the device, as we discussed that we need a p-n junction for a better photodetector. The photodetectors are used in many optoelectronic applications such as optical communication, because optical communication is one of the widely used method in which optics is the heart for the communication medium. Now, when a photon with an energy greater than the band gap, which here we will represent as Eg incident, it becomes absorbed to photogenerate a electron hole pair, and this electron hole pair is free. The electron hole pair is a combination of electron in the conduction band and hole in the valence band. Usually the energy of the photon is such that photogeneration takes place in the depletion layer. We have already discussed about the depletion layer in the previous lectures. The electric field in the depletion layer separates them in opposite direction until they reach the neutral region. The neutral region is the region which is away from the depletion region. These drift carriers generate a current which is called as the photocurrent. Now, the photocurrent lasts till the electrons and holes cross the depletion layer and reach the neutral regions. The photocurrent depends on the number of electron hole pairs photogenerated and the drift velocity of the carriers while they are transiting the depletion layer. Now, since the field is not uniform and the absorption of photon occurs at a distance that depends on the wavelength, the time dependence of the photocurrent signal cannot be determined, and the photocurrent in the external circuit is only due to electrons, though electron and hole both of them are involved in the external circuit, that the photocurrent that we get is due to electrons. Now, let us discuss a little bit about thermal detectors. So, let us consider a simple model to assess the performance characteristic of a thermal detector. The incoming radiation is absorbed by a sensing element of heat capacity H at a rate W. This is connected to a heat sink at constant temperature Ts via a heat conducting element of thermal conductivity G. Now, if we consider a small time interval delta t in which the temperature changes, then one can show that the time varying temperature can be given as delta t as a function of f is equal to W f divided by G whole multiplied with square root of 1 plus 4 pi f square tau h square, where tau h is equal to h by G is the thermal time constant. Now, for good sensitivity, it is desired to have a large value of delta T f. For that, both h and g have to be small, as we can tell this from the expression that we discussed. Small h can be achieved by using thin absorbing elements of small area which has minimal support to reduce g. So, this way we can reduce both h and g. Now, for a good response time, tau h must be very smaller than 1 by 2 pi f. The limiting sensitivity of thermal detector is governed by the temperature fluctuation within the detector. This arises from random fluctuations in the energy flow rate out of the element. Now, let us discuss one of the very widely used thermal detector, which is called the bolometer. It is one of the well known thermal detector. As I said, in the bolometer, the incident radiation hits a fine wire or metallic strip, causing a change in its electrical resistance. This may be detected in several ways. In one way, the element may be inserted into one arm of a wheatstone bridge, and further that it can detect the variation in the resistance. The current through the element must be very small, such that there is no raise in temperature by significant amount, otherwise the filament will be blown up. The main parameter of interest in assessing the performance is the temperature coefficient of resistance, which is alpha, and that is represented as 1 by rho into d rho by dt, where rho is the resistivity and T is the temperature. For metals, alpha is positive, as resistivity of metals increases with increasing temperature. Greater sensitivity can be achieved by using semiconductors, which are called thermistor. The alpha value is negative for semiconductors, as the resistivity decreases with temperature. The other type of bolometer that can be used is carbon resistance bolometer, which can be cooled to liquid helium temperature, and these have been used in far infrared astronomy, as very sensitive detectors are required in that particular application. Here we can use superconducting materials as well, because they can also be having a very sensitive resistivity, which can be varied with variation in the temperature. In operation, the temperature of the element is just held below this value, so that absorption of even small amount of radiation will cause a rapid increase in the resistivity in the case of superconducting materials. This detector is very accurate, but the ambient temperature should be controlled precisely. Now, let us discuss an example of a detector which detects photon instead of phonon, and that is photomultiplier tube. So, this is a photon detecting device. The photoelectrons are accelerated to a high speed between a series of increasing potential electrodes called diodes. So, secondary electrons will be formed after the electrons hit the diodes and hence continue to multiply in number. So, if we take an average secondary electron number as delta and they are emitted at each diode surface for each incident electron, and if there are n diodes overall, then the total current amplification factor between the cathode and anode can be given by the equation G is equal to delta to the power n. Now, electrons take finite time to transit all the diodes, and this time is not same for all the electrons, and there are two reasons for that. And the first reason is there exists a distribution of velocity for the electrons ejected from cathode, and the second one is they traverse slightly different path through the photomultiplier tube because of the difference in the electric field. Because of this transit time, the response of a photomultiplier tube is limited when a fast optical pulse is shown on it. A change in design may resolve these two issues. Now, having the change in design regularly, the photomultiplier tubes with rise time of 2 nanosecond and transit time of about 30 nanosecond are widely available. Photomultiplier tube also suffers from external noise, and the different types of noise which contribute towards the less amount of photocarriers are the following. The first one is the dark current noise. This is the current in the photomultiplier tube when it is not exposed to light, and this is mainly due to thermionic emission because of the presence of the heat. The thermionic emission current for a cathode at temperature T of area A and work function phi is given by I T is equal to alpha A T square exponential minus E phi by k T, and this equation is called Richardson-Dussmann equation, and here the alpha is a proportionality constant. So, the thermionic emission can be reduced by reducing the cathode temperature, because it is mainly because of the temperature or the ambient temperature which may increase because of various other reasons. If we reduce that, then this noise can be reduced. But even if we reduce this, there are other noises which can dominate in low temperature, and since the dark current is not absolutely constant as it is subjected to random fluctuation, so it cannot be deducted from the final output current, and however the current itself subject to fluctuation due to the statistical nature of thermionic emission. Now, the other type of noise that can contribute to the less amount of photocurrent or the less transit time is short noise. So, short noise is another type of noise which is due to the fluctuation in the flow of electron at a point in the circuit, and the magnitude of root mean square current fluctuation with frequencies between f and f plus delta f is del I s is equal to square root of 2 I e del f, where I is the current flowing in the circuit. The presence of dark current limits the detection limit of photomultiplier tube, and which can be written in the following way, that is W mean is equal to square root of 2 I t e delta f divided by r as a function of wavelength. Now, the anode current noise gives rise to multiplication noise, and the thermal agitation of charge carrier in the conductor gives rise to Johnson noise. So, these are the other two types of noise, that is the anode current noise and Johnson noise, which can also contribute to the less or the higher transit time for the electron that is there in the photomultiplier tube. So, the next detector that is also that can detect photon is charge coupled device, which we will discuss. In this device there exists a photoactive region which is usually silicon and a transmission region made from shift resistors. So, when an image is projected onto the capacitor array, causing each capacitor to accumulate an electric charge proportional to light intensity at that location. Now, once the array has been exposed, a control circuit causes each capacitor to transfer its contents to its neighbor, which operates as a shift resistor, and the last capacitor in the array dumps its charge into a charge amplifier, which converts it into voltage, and this will be repeated till a circuit converts it to digital signal. So, this way a photon which is projected or which is shown on the array of capacitors completely forms the digital signal. This is how the process goes in. Now, there are two important parameters which quantify the operation of a photodiode. Whether a photodiode is good or bad can be decided by analyzing these two parameters, and they are called quantum efficiency and responsivity. So, what is quantum efficiency? So, as we expect, when we shine light of a particular wavelength on the detector, we expect all the photons to form electron hole pairs and to get disintegrated to go to the external circuit as the photocurrent, but not all the photons incident at the junction create free electron hole pair that can give rise to photocurrent. So, the efficiency of conversion process is given by quantum efficiency, and it can be defined in the following way, that is quantum efficiency eta is equal to number of free electron hole pair generated and collected divided by number of incident photons. Now, let the number of electrons collected per second is IPH by E, where IPH is the photocurrent. If P0 is the incident optical power, then the number of photons arriving per second is P0 by h nu. So, the quantum efficiency now becomes eta is equal to IPH by 2, or rather IPH by E divided by P0 by h nu. Not all the free electron hole pair can be collected. Some of them will recombine and get lost, and it also happens when semiconductor length is comparable to the penetration length. So, the quantum efficiency can be increased by decreasing the reflection of semiconductor surface, by increasing absorption within the depletion region and preventing recombination in the traps. If we follow these 3 steps, then we can increase or enhance the quantum efficiency of the device. The next parameter that we want to discuss is called responsivity. So, the responsivity R of a photodiode characterizes its performance in terms of photocurrent per incident optical power at a given wavelength. So, R is equal to photocurrent divided by incident optical power, and that is equal to IPH by P0. From quantum efficiency we can write R is equal to eta E by h nu, or it is equal to eta E lambda by h c. So, the responsivity depends on the wavelength of the light that is shown on the detector. It is sometimes called as spectral responsivity or radiant responsivity. Now, we will discuss different types of photodiodes that are widely used for various applications. The first one is PN photodiode, though we have discussed little bit about the principle, but let us go into the structure of this PN photodiode. So, it has a P plus and N type of junction, that means one side is P plus and the other side is just N type material. This means the acceptor concentration in the P side is much greater than donor concentration in the N side. The P plus side is generally very thin and is usually formed by planar diffusion into N type epitaxial layer. Across the junction there are space charges called depletion layer or space charge layer, which we have already discussed. The depletion region almost extends entirely into the lightly doped N side. The photodiode is normally reverse biased and the reverse bias drops across the depletion region. Next we will discuss PIN photodiode or P type insulator N type photodiode. It is a photodiode having a P plus intrinsic N plus layer, and the intrinsic layer is having much smaller doping than the other 2 layers. The charge carriers diffuse into the depletion region from both the sides where they recombine. So, the charged acceptor and donor ions will give a uniform electric field across the junction. The junction or depletion layer capacitance of PIN diode is given by C dip is equal to epsilon 0 epsilon R A divided by W. Since the width of depletion layer is fixed, the capacitance does not change. And in PIN photodiode, the photon absorption occurs over the intrinsic layer, which is between the P and N type material. So, the electron hole pairs are then separated by the electric field and drift towards the N plus and P plus sides respectively. The response time of the PIN photodiode is determined by the transit times of the photogenerated carriers across the width of the intrinsic layer, and that is T drift is equal to W by V d. To increase the response time, we have to decrease the drift velocity. Now, the final type of photodiode that we want to discuss is avalanche photodiode. So, these are widely used in optical communication because of their high speed and gain. There is a N plus layer along with 3 P type layers to maintain the field distribution across the diode. The diode is reverse biased to increase the field in depletion region. The absorption of photons and hence photogeneration take place mainly in the middle P type layer. Here the electrons get accelerated in the high field and causes impact ionization, and these electrons which are generated due to impact ionization again cause avalanche of impact ionization and create more electron hole pairs. So, gain is due to a large number of electron hole pairs formed by a single photon, and avalanche multiplication factor M of an avalanche photodiode is defined as M is equal to multiplied photocurrent divided by primary unmultiplied photocurrent, and that is equal to IPH divided by IPHO, where IPH is the multiplied photocurrent and IPHO is the photocurrent in absence of multiplication. For a small reverse bias, empirically we can present or we can represent M as M is equal to 1 by 1 minus VR by VBR to the power n, where VBR is the reverse breakdown voltage and VR is the small voltage that one can apply, and n depends on the temperature. So, viewers, today what we discussed in this session can be summarized by the following few important points. So, we started the discussion about the principle behind a photodetector, then we discussed about a thermal detector and how a thermal detector can detect a thermal signal, and one of the examples that we consider is a bolometer. Then we discussed few examples related to detector which detects photons instead of phonons, and those examples are photomultiplier tubes, and we try to understand how or what is the principle of photomultiplier tube. Then we discussed in detail the charged coupled devices or CCD devices, which are the heart of any digital camera that we see around us. And then we discuss the different types of photodiodes, that is structurally we can have different types of photodiode. They are either PN junction type or PIN junction type or avalanche type. So, three of them have their different characteristic structure and features, and they are used for different purpose in different situation. And finally, we discuss the two important parameters which defines the quality of the photodiode or photodetector, and they are the quantum efficiency and responsivity of the devices. So, viewers, I hope today's session would help you gather more knowledge about photodetector and their application, and thank you very much for your attention.